So, good morning all. Am I audible?
Yes, sir.
Okay. So, in the previous lecture, we were discussing about we used EPMC instrument to design ammeters, multi-range ammeters, and then we also discussed about how to design voltmeter also using PMMC, even though it is a current measuring instrument, right? So, to briefly recap what we did in the case of a DC ammeter is we basically utilized a series multiplying resistor RS, right? And this is our model of meter, PMC meter. And if we wanted to measure the voltage across these two terminals, then we connected it and we calculated the value of RS depending on the range which we need for the voltage measurement, right? So because the typical range is basically V is equal to Im into Rm, where Im is the full scale deflection current associated with the meter. When you multiply it with Rm, that is the voltage only this part can measure if I consider only this. So to extend the range, we needed a series multiplying resistor. So we took an example also and how one can utilize this equation to evaluate the required value of series resistance based on the given voltmeter range, right? That is what we saw, and we also discussed about what is voltmeter sensitivity. It is associated with the total resistance divided by the full scale voltage, right? So now we also said that the similar to ammeter, one can utilize the number of series resistances connected in parallel with each other to give the user flexibility to choose the range, right? So the based on this same thing, if we extend it, let's say this is my meter resistance, this is my meter. So instead of single resistance, if I consider multiple resistances which are connected in parallel, right, and give a single pole multiple throw switch connected in series with this to the user, then the voltage across these two terminals can be measured depending on user selected range, right? So these are all multiple playing resistors R2 and R3, right? And A, B, C, D. Right? And also we have seen another configuration. So this is a parallel configuration, and we have seen that there is another configuration wherein instead of connecting parallel resistances in parallel, you can connect them in series in this manner, right? And you get the different taps from the terminals of the series resistances R1, R2, R3, and then give a switch to the user. This is also Rm. Okay. Now all of these are multiplied resistances. Please remember. Now, which one to choose? Which is a better option? So that will become clear if you consider an example. So consider your Im. So I'm treating Im as my IFSD is 50 microamperes. So this meter which is there has maximum deflection for 50 microampere current, and the resistance associated with the meter is 700 ohm. Now we would like to design a voltmeter which has these three ranges: 10 volt, 50 volts, and 100 volts. Right. So if we utilize this, then if I consider this circuit first, and this is B. So in the case A, how will you design the value of R1, R2, and R3? What will be the value of R1? It will be V divided by Im minus Rm. Now, for in the case of R1, okay, my voltmeter range I need is 10 volts. So R1 is 10 divided by 10 volts divided by 50 microampere minus Rm is 1700 ohms. Okay, so can you tell me what is the value of R1? What is the value of R1? Can you someone please calculate?
$18,300.
Sorry,
18,300.
18,300. Is it this much?
Yes, sir.
Okay. Similarly, substitute 50 volts here in this place to calculate R2. Will it be this small? Because this is volt in microampere, no? So it will be on the scale of 10 raised to 6. Minus
So
something
something like 200 kilo something.
198300.
198. Okay, it is 198. Okay, now it makes sense, right? Because this is 10 raised to 6, no? 10 raised to 6 range. So R1 is 198.3 kilo. What is, how much is R2? For calculation of R2, simply use. Sorry. Hello. Sorry.
So nearly 1 mega ohm.
Approximately 1 mega ohm. What is the exact value?
998.3 kilo.
And what is R3? Here you use 100 volts.
So 1.9 sir 1.9983 mega.
Mega.
Yes, sir.
Okay. Now you use this configuration now. Configuration B. Okay. So in the configuration B, when the switch is in position here, let's say A, B, C, D, in the position of B, the calculation remain the same, right? So R1 is still 198.3 kilo. What about R2? What about R2?
800,000.
800 kilo ohm, right? Why? Because in the calculation of R2, you need to do 50 divided by 50 volt divided by 50 microampere minus 1700 minus R1, because it will come in series, right? So the combination will be R1 plus R2. So it is coming as this thing. And how much is R3?
So mega, 1 mega.
1 mega. You see the difference here, that apart from this resistance, these two resistances come out to be different because of the change in configuration. Now, which one is better to choose? Configuration A or B?
Perhaps series maybe.
Why?
So because I think these resistances are a bit more easier to find than these.
Yes. So you see, these are the values which has come out are easily available from off-the-shelf components, like off-the-shelf resistances. You can obtain these values, whereas these are very specific values. So if you want to design, because remember we are designing an instrument, right? So the performance of the instrument depends on the component values. So in this configuration, instead of this value, let's say if I choose 990, or let's say somebody said approximately 1 mega ohm, right? So in that case, the calculation will go wrong. The calibration will be incorrect. we have to use this exact value. So in that case, these resistances need to be manufactured separately, which is a costly affair. Right. So on the other hand, these are the calculation itself has come out to be the values which are easily available. So in that case, the configuration B is preferable over configuration A. So these calculations are very simple. You can expect such examples in your exam. Now, apart from the DC voltmeter, if you remember, we were talking about DC voltmeter and DC ammeter. But can we utilize the same PMMC instrument for the measurement of AC quantities? Okay, so in this case, as you can see, the example is shown here. Let us now first look at the working principle of this rectifier voltmeter. So this portion remains the same. This model of the meter PMMC instrument remain the same, whereas the previous portion is now slightly different, as you can see. In this, remember, our PMMC instrument is polarized or non-polarized. Is it a polarized instrument or non-polarized instrument?
Polarized.
It is polarized. Means, what does it mean by that? You see here, it is marked plus and minus, right? So you have to apply the current that to be measured in this direction only. Otherwise, either you will not get the reading, of course, but you may also damage the instrument if you pass the current in opposite direction. So it is a polarized instrument, and since we are trying to utilize it for AC measurement, which has both polarities, positive and negative, one has to first rectify the AC quantity before its application to the PMMC instrument. Okay, so you can see that. Have you studied a rectifier in previous course, basic electronics?
Yes, sir.
Yeah.
Yes, sir.
So this is then you can easily make out that this is a full wave rectifier circuit which utilizes 4 silicon or germanium diodes, where the diode D1 and D4 conduct during the positive half cycle of the input AC quantity. Right. So you can see when this is positive and this is negative, then the current will flow through RS, through D1, and then through the meter in this direction, which is shown here, and then through D4 to the negative terminal. And in the second half cycle, when this is positive and this is negative, then D3 will conduct and the direction through the meter remain the same, and D2 will conduct and then it will go through the negative terminal. Excuse me. Yes. So yeah, so we this rectifier circuit makes sure that the current through the meter. Now, if you remember, in the rectifier circuit, the purpose was to convert AC into DC, right? So it is the same thing here. We converted AC into. So is this DC the output voltage, or here is it DC, or what you call it as? It is a pulsating DC quantity. Okay, it is pulsating DC. This it is not constant DC. It is a pulsating DC. Just that it is positive, the meter will indicate some value. However, remember the PMMC instrument design. If you can remember that it is an electromechanical instrument, right? So it has its inertia and damping associated with that. That's why we represented it is with the second order instrument, right? A second order system. So in that case, there if we also studied the frequency response of the second order system. So in the case of PMMC, if the applied input AC, applied pulsating DC is slowly varying, like on the scale of less than 1 Hertz, let's say, then the meter, you see, let's say the meter is like this. Zero position is here, the full scale position is here, so it is zero. This is full scale deflection current. So when the positive cycle goes from here to here, so probably it will go from this position to this position and come back to zero. Okay, in this, and then in the next cycle again it will do the same. It will go on oscillating depending on the pulsating DC and the frequency associated with that. But in general, when you work with 50 Hertz signals, which is the typical frequency range of our household AC quantity, AC input supply, the 50 Hertz frequency is too much for the PMMC instrument to respond. Okay, so in that case, it will basically stabilize to a particular value. Stabilize to a particular value. Now, if you don't supply positive quantity only, but if you, let's say, don't use rectifier circuit and directly apply an AC quantity, and imagine that the AC quantity magnitude is small enough not to damage the meter. Okay, so in that case, what will happen? That the instrument will settle, means what when I'm saying instrument, the pointer, the pointer in of the deflecting instrument will settle to zero value, or the average value of the input. Now, what is the average value of sinusoidal signal? It is zero, right? So it will settle down to zero. It will not show any particular fixed value. But remember, it doesn't mean that there is no current flowing through the instrument. Current is still flowing through the instrument, just that it is not able to respond to the rapid variation of the current. The average value it will indicate it as zero. Of course, we are assuming that my supply is purely sinusoidal. But in the case of rectified signal, where we have a pulsating DC, where the pulsating signal is always positive, then the average value is non-zero. Okay, and what is that average value? The average value in that case is equal to 0.637 times the peak current value. Okay, peak current value. So IP represents the peak current, I RMS is the RMS value, I average is the average value of the current. Okay, and all these quantities are related to each other, and the peak current is related to average value with this expression, where it is 0.63 times of the peak current, whereas RMS is 0.707 times peak current. So you know where this value comes from? Where does this value come from?
Since we take root, it will come.
Sorry?
Since we take square root, it will come
right
from there.
So you have already studied RMS quantity, what is RMS, what is average, and then you can establish the relationship between RMS and average also, where 1.1 times average value is the RMS value. Now, since these relations are really linear, you can calibrate your instrument either to measure average value, because basically remember, your meter will, in the absence of calibration, it will always indicate average current. Okay, however, using this relationship, you can calibrate the instrument to measure RMS current directly. RMS is the value we are mostly interested in. Can someone tell why we are interested in RMS? Why we are always interested in RMS but not?
It would involve all the values like positive and negative, and it would not have. If we take average, it would may give us zero.
What is the physical significance of RMS value?
That would be what the response that the instrument will show.
No, in general,
DC equivalent.
don't think about instrument from instrument perspective. In general, what is the physical significance of
DC
Also
Power
useful for
used.
power. It's
Power used.
sorry?
for power
Is it-
calculations. It's
No. Be more specific. Power calculations means what?
Power consumed.
Power consumed means
it is nothing but a DC equivalent.
yes. What did you say? What did you say?
DC equivalent.
DC equivalent. You complete
Power
the
consumed.
answer, no?
Same amount of power would be dissipated. This is equals to IRMS.
Right. So it is the quantity which is equivalent to DC in a sense that same amount of power will be dissipated in the load when you apply the equivalent DC value, right? So in this case also, that's why we are interested in RMS. So usually the meters are calibrated. Is the screen visible? I actually shared it again. Now it is
yes, it's
visible.
visible.
Okay.
Yes.
So it is mostly VRMS and IRMS are the quantities with which the meters are calibrated. Okay. So the 230 volt, which we say in our household applications, which we use, 230 basically represents RMS only. Okay, 230 is RMS value. So then you can now see that apart from this portion, the other portion is the same, right? Multiple register is in series with the meter, right? In series with the meter, just that this portion is included to rectify. Now we need to perform some calculations in order to evaluate the proper value of RS, which need to be connected in series for the AC quantity measurement. Now again, AC quantity, when we say, they are also usually expressed in terms of RMS. So please remember, whenever you are told that you have to measure voltage of 100 volts, if it is not specified whether it is peak, RMS or average, you have to take it as RMS value. That's why I put it in bracket. So if in the exam, if you are asked design a voltmeter for the range 0 to 100 volts, please take this 100 volts as a RMS value. So if we are designing a voltmeter for 100 volts, let's say, with a meter which is having full scale deflection of 100 microampere and the meter resistance of 1 kilo ohm, then you are asked to calculate the value of series resistance that need to be connected in series. Now for that calculation, remember that your meter must withstand the peak current that will flow through it. Okay, even though it will respond to average as an average value to the supplied current, but uh, it should withstand the peak value. So all the calculations in this case must be done considering the maximum voltage or peak voltage. So what is peak voltage in this case? What will be the VP value? It will be 1 point square root of 2 into VRMS, right? So what is this value? How much is this value? 1.414 into VRMS. VRMS is this 100 volts. How much is this?
141.4.
141.4 volts, right? Now this voltage is here. Now remember, this is instantaneous voltage. Instantaneous voltage. So we are calculating the values for instantaneous quantities. The reason being they should withstand to the maximum value. So this voltage is getting divided across the voltage across RS, voltage drop across D1 and D4 in the first positive cycle, let's say. In second, it will be this thing, but the calculation remain the same for both. So D1 and D4, and then the voltage drop across meter, right? Now you have to subtract the voltage drop across the diode. So in general, if you consider silicon diodes, how much is the voltage drop across a diode when it is forward biased? 0.7. So VF is 0.7. So 2 into VF, because there are two diodes which will be in conducting mode in that case. So 0.7 into 2, 1.4. So Vp minus 1.4 divided by the total current that will be calculated now, which is flowing through this entire circuit, that is Rs, D1, this D4 and out. So the peak current can be calculated by the voltage supply Vp, peak voltage minus the voltage drop across this divided by the total resistance. What is the total resistance? It is series connected resistance Rs plus Rm. So that is my peak current. So how much is this peak current? Can someone tell? So do 141.4 minus 1.4 volts divided by Rs plus Rm. Rs is not known. Okay, Rs is not known. So Rm is known. So you have to calculate Rm. Now, what is the peak current? What is the peak current the meter can withstand? And how can we calculate it? What is the extra information which is given? Rm is utilized, V is utilized. We are not utilized IFSD yet. Now, what is IFSD? 100 microampere. But what does it indicate?
I mean, at this much current, we should get peak value.
No. What did I tell? The meter will respond when the meter shows 100 microampere. What value is it showing?
RMS?
No. It is showing average value. Isn't it? I told you, meter, when meter shows for the DC quantity, even though it is pulsating DC, what it is showing is the average value. Means I average is maximum average is 100 microampere. Okay, maximum average is 100 microampere. So then what is the corresponding peak current value? If 100 microampere is the maximum average value, what will be the corresponding maximum peak value?
Calculate
1.637.
Sorry.
157
microampere. Right? 157 microampere is the maximum peak current that will flow through the meter. Okay. Now we have this quantity. So IP, we have this quantity. So what is 141.4 minus 1.4? How much is this?
140.
Huh?
140.
140. Now 140 divided by IP will give me what? Rs plus Rm, right? So how much is this? 140 divided by 157 microampere.
Something like 891 kilo.
891 kilo ohm.
Yes.
Okay. Now subtract Rm from this, which is given, which is 1 kilo ohm. That will give me Rs as 890 kilo. Right? Now you have to substitute this resistance in series here along with these diodes so that your meter now can be calibrated to measure the RMS voltage from 0 to 100 volts. Okay. Now remember, in this calculation, the values are derived considering the instantaneous maximum instantaneous voltage, that is peak value. Please remember this, that how one should calculate the component values. Now, okay, fine. Now there is a limitation of this, not limitation, but it may go in. It will be incorrect in the case when diodes are not biased properly. What do we mean by that is that below knee voltage, we know that the if the so to operate the diode beyond knee voltage, so in the linear range, we want to have some current that need to be passing through the diode, so that it will be the voltage drop across diode will be beyond knee voltage and it will be operating in a linear range. However, some cases what happens is that we know that the drop will also depend on the supply voltage. So here it was 100 volts, that is fine. Maximum voltage is 100 volts, but in a lower range. Hello, am I audible? Hello.
Yes, sir.
So in a lower range of the voltage, let's say the voltage you are measuring is 1 volts or 2 volts. What will happen is that the diodes will not be properly forward biased. Okay, so then the voltage drop will be different than what we considered during this calculation, right? So once this voltage drop goes less than 0.7 or some, it is not the same, then the calibrated value will be different, right? So the reading which we will take will be incorrect. So in order to ensure that even at the low voltage, the diode will be properly forward biased and the voltage drop across them remain 0.7 as used in the calculation of the component values, we need to make sure that certain amount of current must flow through the diode. Okay, so in order to ensure that that much current should flow, remember that current will flow through the meter also, right? But meter may not withstand that much current. So the option for that is that similar to what we did in the case of emitters, that provide the alternative path for the current to flow bypassing the meter. So in this case, we will consider the rectifier voltmeter example with half wave rectification. Remember, the same approach will remain, just that with this example we will also explore the utilization of half wave rectifier voltmeter also. So previously we saw full wave rectifier. So let us see, the series resistance remain the same and the meter resistance and the meter remain the same in this. So the voltage will be applied across this, just that we need to insert one rectifier. So previously we had inserted this full wave rectifier. In this case, we'll only insert a half wave rectifier. So this will be my D1, this will be my D2. So the voltage that to be measured is applied here. Again, it is a sinusoidal voltage. So this is the series resistance, diode D1 meter with resistance Rm. Current is flowing through this. Now, how the pulsating DC current will look like? In the positive half cycle, this will be positive, this will be negative. So the current will flow through RS forward biasing D1 and in this direction, right? In this direction. And what happens in the negative half cycle when this is positive and this is negative? What will happen in negative half cycle?
It will flow through D2.
The current will flow through D2. That means it will bypass this portion. The reason is, in that case, D1 will be reverse biased, right? So the current will not flow in this. So if we plot versus time, the current flowing through the meter, it will be this, right? So this is my peak current. Some average will be this. RMS will be equivalent. can be equivalently calculated. So in this case of half wave rectifier, average current in the case of full wave, it was 0.637 times IP, right? Now since there are only we are skipping one cycle, so the average current will be 0.5 times the average current associated with full wave rectification. Okay. Now if you consider this now, then what we can do is, in order to allow some minimum current that must flow through the diode, as I mentioned, you consider an shunt resistance RS which is connected in parallel with the meter, which will take the extra current that is supplied through the diode, and it will bypass that portion of the current from the meter, so that meter will not get damaged. So that this is the arrangement which is made to ensure that minimum current will flow through the diode, for that, so that it is beyond knee voltage, and we consider 0.7 volt as the voltage drop across that, and at the same time providing the bypass around the meter. So when can so this value comes out to be 0.3185 into peak current. So let's take an example, and in order to evaluate what should be the value of series resistance and shunt resistance also. So the specifications are given such that the meter full scale deflection current is 50 microampere. Okay, IM or IFSD is 50 microampere. The meter resistance is 1700 ohm, and you are asked to design a voltmeter with full scale deflection of 50 volts, again specifying RMS value. And we are designing it with a half wave rectification, wherein we need to ensure that 100 microampere must flow, minimum 100 microampere. Okay, minimum 100 microampere must flow through the diode when the meter is measuring 0.2 times the full scale voltage deflection. Okay. Now, what is 0.2 times full scale voltage that will be measured? We are asked to measure up to 50 volts. What will be 0.2 times of that? It will be 0.2 times of that. 10 volts. What does it mean is that when we are measuring 10 volts RMS, diode must be biased such that minimum 10 microampere is flowing through that. This is the specification given. So since this current and the voltage are linearly related in this circuit, what we can say is that for 0.2 of full scale deflection, that is for 10 volts, if the required current through the diode is how much is 100 microampere, when it is 50 volts, means at the full scale deflection, how much is the current required? How much is the current required? Minimum current
500.
500. 500 microampere, right? So this 500 microampere will flow through the diode. Now you tell me this 500 microampere is representing peak current or RMS? So this is peak current. So this 500 is also indicating peak current. I peak. Okay, is 100 microampere. Sorry,
Right.
500 microampere when the 50 volt RMS is applied. Now, when 500 is flowing through this full scale deflection, what is the full scale deflection current of the meter? What is the full scale deflection current of the meter?
50.
50 microampere. Now you tell me this is average or peak?
Average, sir.
Average, right? Now calculate the corresponding peak current. And since it is half wave rectifier, it will be this much. So calculate I peak. 50 divided by
156.9.
156.9
8.
microampere, right? So now you have all the quantities. That what is peak voltage? What is peak voltage? What is peak voltage? 50 volt is given as RMS, no?
141.44.
One, no, why 41.44?
70.7.
Yeah, it is wrong, no? So I write 1.414 into 50. That will be my peak voltage, right? So it is coming out to be 70. How much?
70.7, sir.
70.7 volts, right? We have peak current, peak voltage. We have peak current also, which is flowing through the meter. Now we have calculated this thing. So 500 peak is flowing through the diode. It is getting split here, right? So 157, approximately 157 is going through the meter. The remaining is going through this resistance. How much is going through the resistance? Then what is ISH? 500 minus 157. How much is it? Huh?
343.
343 microampere. Now we have ISH, we have I peak, which is flowing through the meter. Let's say IPM. Now can you calculate RSH? Can you calculate RSH? Is it true? ISH into RSH is equal to I peak into RM. Is it true? Is this relation true or not? Hello?
Sir, they are in parallel, so
So it is correct, no?
yes, sir.
So what is RSH then? I know this value. No? It is 157. RM is given, that is 700. ISH is 343 microampere. So what is the value of RSH?
778.
778. You should also always mention units.
0.134.
Huh?
0.134.
What point? What?
778.134.
134. What is the unit?
The normal, just ohm.
Yeah, you should say the unit kilo ohm or ohm or something like that.
Just ohm, just ohm.
Yeah. So in the exam also, please remember this is the very frequent mistakes are done during quiz and all. Please mention units. The simple number will not carry any information. Okay, fine. So 768 ohms. Now we have to calculate RS also. How can you calculate RS? So consider this circuit, this part. So V peak minus VF, single diode is there, right? Minus the voltage drop, or yeah, V peak minus VF
minus
minus
IPRM.
IP
RM.
RM. This will be the voltage across which resistance?
Because RS.
RS. And how much is current flowing through the RS?
Add ISH and IPM.
That is 500 microampere.
500.
How much is this value? Vp is already calculated, 70.7 minus 0.7. So 70. 70 minus IPM into RM. Yeah. Divided by 500. How much is this?
$139 kilo ohm.
139 kilo ohm. Fine. You see, now we could able to calculate RS as well as RSH based on the given specifications. Right. So the RSH is helping the, so you see what is the current it can withstand meter maximum peak current it can withstand is 157 microampere. But the required current for the proper biasing of the diode was 500 microampere at peak value. So where does this 343 microampere should go through? It will go through the shunt resistors. Okay, so this is how one need to do the evaluation of circuit components.
So
Remember
why did
the
you
same. Yes.
take, so why did you take ID minimum as the peak?
Sorry. Here.
You took ID minimum as peak, yeah. Why did you take it as peak?
Because as I mentioned that it is the peak current that is minimum which is required for forward bias. Because you see we are always calculating at instantaneous value, right? So
Yes,
at
sir.
the peak supply voltage the current flowing through the diode will be peak current, no?
Yes, sir.
Right. So that required minimum is 100 microampere. That is specified.
Okay, sir.
Okay. Okay. Now, in a similar approach, the way we did with the the rectifier voltmeter, one can also design the rectifier ammeter. Now, in this case, in the case of rectifier ammeter, one must remember that the current which we are trying to measure is AC quantity. The current is AC. We are trying to measure, and many times we have seen. So in the case of ammeter, what is the requirement of an ammeter in terms of the loading effect? What should be the resistance offered by the ammeter?
0.
Yeah, ideally it should be 0, right? Now, you see that, and what is the voltage drop across ammeter called as? We used one word term there. Voltage drop across ammeter. Ideally, it should be 0, but practically it is some value which is called as burden voltage, isn't it? Right? It is called as burden voltage. Now you see, in the case of rectifier ammeter, if I use rectification using the, let's say, if I consider full wave rectification, the voltage drop across will be significant, no? 1.4 volts only across diode, right? So in that case, the burden voltage will be significant, so it will not basically satisfy the criteria for a ammeter, ideal ammeter. So in that case, what is done is we use current transformer, okay, which will give the ammeter the required low resistance as well as it will step up the voltage to operate the voltage drop across the diodes. Okay, so let me simply draw. So in the case of current measurement, so this is the current we are trying to measure. Okay, this is primary current of the current transformer, and you have more and more of terms in the secondary, which will create the secondary current. Okay, secondary current. Now here there will be stepping down of the primary current and stepping up of the secondary voltage. So primary voltage will be stepped up, but and secondary voltage, sorry, the primary current will be stepped down with the current transformer. Now in this, what it's done is this secondary current is passed through a load resistance RL to generate a voltage here, generate a voltage here that will be measured with our previously designed full wave rectifier. Okay, voltage. Now you see voltage is generated here. So let me say VL. This voltage is now measured with our previous design of voltmeter. Your meter is connected across this. So this is my D1, this is D3, D1, D4, D2. So you see this portion is your previously designed full wave rectifier voltmeter, right? And this arrangement, this part is designed for converting the current into voltage, and to voltage to a certain level that it will be able to drive the diode so that it can provide the required voltage drop across these diodes. So this is a very this is arrangement which is made for converting this into rectifier. Now the point is that in this case also, sorry, this is series resistance. So in this case also one has to come up with the required value of RS and the required value of RL based on the specification which is provided for the current measurement. What is usually given is the full scale primary current that you need to measure. So you are asked to measure the current from 0 to 250 milliampere. Okay, and the full scale current which the secondary that will measure will be 1 milliampere. Sorry, not secondary. This is IFSD associated with meter. So this is IFSD associated with meter. And what is also given, sorry, is how many number of turns are there in the primary and how many number of turns are there in the secondary. NF and NP and NS represent the number of turns. So what is the ratio and what is the relationship between primary current and secondary current and primary secondary number of turns is given by this. They are they are inversely proportional, right? So if NS and NP is given, what will be the secondary current? What will be the value of IS? It will be NP divided by NS into IP. So what is NP? 4 divided by 500 is the secondary number of turns into what is primary current which is given 250. Now can someone tell this 250 is RMS or peak?
Average.
No. What did I tell? When you design anything, if you remember, we were designing 100 volts, no? 100 volts, and here we were designing for 50 volts. In bracket I written RMS. And what did I mention? If nothing is mentioned, what value you should take? What value you should take?
RMS.
RMS. So this is RMS. Okay. So when primary current RMS is 250 milliampere, what will be the secondary RMS current?
2 milliampere.
2 milliampere. 2 milliampere. Right. Now, this IFSD 1 milliampere is what? Which value? Average, RMS, peak.
Average.
This is average. Average flowing through the meter. Then what will be the peak current or RMS current that will flow through the meter? IRM average is 1. IRMS is how much? 1.11 milliampere, right? IRMS. What is I peak? How much will be I peak?
1.57.
Sorry?
1.57.
1.57 milliampere. Okay. Now, in this case, 1.57 milliampere is the peak current which is flowing through this, through the meter. Now, what will be the value of VL? VL peak. What will be VL peak? It is the peak current flowing through this, and this same current is flowing through the meter, right? And how much is flowing? 1.57. So IP into, it is flowing through RS and RM both. So RS plus RM plus 2 times the voltage drop across this, that is 2 into VF. Isn't it? Now one more thing is mentioned. RS is given, RM is also given. You have just calculated I peak that will flow through the meter, 1.57 milliampere into 2 into VF, which is we consider it as 0.7. How much is this? How much is this?
35.4.
35.4 volts. Now this is peak voltage. What is VL RMS? This is
20,
peak.
25.
25 volts. Okay. Now you see this VL RMS is across RL. Right? Isn't it? And how much current is flowing through RL?
IS minus I peak.
Are you sure? Are you sure? How much is flowing through RL? Are you consider IS is how much? How much is IS? Tell me. How much is IS?
1.4.
No. IS is 2 milliampere. Is this RMS we calculated or peak?
RMS.
It is RMS, no? So when you are using RMS here, this quantity flowing through in this part should also be RMS, no? You can't subtract RMS from peak value from RMS, right? So you have to subtract 2 milliampere, that is peak current in the secondary, sorry, RMS current in the secondary minus RMS flowing through the meter. How much is RMS flowing through the meter?
1.11.
1.11 milliampere. Then this will be the current flowing through RL. That will be RMS current flowing through RL. Right? How much is this? Can someone quickly tell?
0.89.
0.85.
89, sir.
89. 89 milliampere that will flow through RL. What is the voltage across RL? RMS. 25 volts. So 25 volt divided by 0.89 milliampere will give me value
28 kilo.
28 kilo. You see, we could calculate this. This calculation. Okay. So we'll continue in the next class. Okay. So please remember, Monday will be your quiz. Thank you. I
Sir,
will
if you
give.
can
I will.
tell which reference you are using, it would be useful, sir, for these slides.
Yeah, this one I have every slide at the end of the slide I'm mentioning.
Sir, could you upload the lecture slides?
Yeah, I will upload it today. Yeah, I will upload it. Thank you.
Quiz will be up to which lecture? Again?
10th lecture.
Okay.
So how many marks total will it be?
Total, I will mention. I will tell you. All the details I will mention
Okay,
in
sir,
the Teams group. Yeah.
Thanks, sir.
Okay. Thank you.
Thank you, sir.
Thank you, sir.